Perfect. So what we usually do is we get the team to just give a high-level presentation about themselves, or if they want to go into more depth, that would be great as well. I think a lot of Subnet Summer would be curious about what this subnet is, what the miners do, where the validators step in, what the roadmap is like, what the success plan looks like. So yeah, it'd be great to hear from you guys. What at core, in one sentence, what is ChipForge?
Can you hear me? Am I audible?
Yes, I can hear you.
And I'm not too loud, right?
No, you're not. If one of you guys want to turn on your camera, that would be fantastic. But if not, that's fine.
I'm basically going to share my screen because we have built a short presentation.
Perfect. Thank you.
Yep. So my screen is visible.
Yeah, that's great. Thank you for that.
Okay. Okay, I think so. Let's start. I would try to walk you through from the start how we started building ChipForge. So basically, when we started exploring Bittensor and we started basically working on Bittensor, we always wanted to build something meaningful. And by that time, there were many subnets which were doing good in AI, basically in training models, running agents, processing data. They were basically pushing the boundaries of decentralized AI, right? But we, from the start, from the very beginning, we had one clear rule in our mind that whatever we build, it has to be completely unique. Okay. So we basically wanted to find the gap nobody else was looking at that time. So we, kept trying different things, and then this idea finally hit us that all of these subnets, every model, every agent, and every inference call, what actually runs all of it? And obviously the answer was obvious, the microprocessor chips. And nobody else in the community was touching this side at that time. So the moment this idea hit us, the team was aligned, and we were sort of, sure that we would definitely give it a try. So we started building the subnet, and when we got deeper into our R&D, we quickly realized that why nobody had done this before. This is a highly centralized industry on the planet. A handful of companies control it, and basically they have billions of dollars in budget, and they have years-long development cycles. They have NDAs at every turn. So it is basically a walled garden. Okay. So, but we thought that there's always a first time for everything, right? We sort of knew, it seemed like that it was sort of punching above our weights, but we kept, trying different things and building, and we finally made this subnet, which is now called ChipForge. So this is how ChipForge works at a high level. It works in 4 steps. The first one is that we basically make a challenge, a hardware challenge, a structured challenge in which we explain all the requirements of the challenge. And at this point, we also make 2 test cases data sets. One is for miners and the other is for validators. And we try to cover all the corner cases, all the boundary conditions in these data sets. So the miners download the challenge requirements along with their test cases, and the validators download the test cases which are designed for them. So after that, the miners and AI agents start competing with each other to produce the best design. And when they are done with the design, they submit it to the server, and then these designs are sent to the validators from the server. And once the validators are done evaluating these designs, they submit the score back to the server, and they also set the weights on the blockchain. And that's how the best design earns the reward in terms of tau. Okay, it seems simple, but guys, this is not simple. It is extremely difficult for us in execution, and this basically difficulty comes mainly from one aspect of our subnet, and that is validation. Now, let me explain it in a bit detail why this is the hardest part. So basically, our validation, I think, let me put it this way, that the validation that we do in hardware is completely different from the validation we do in software. So in software, what we usually do is specifically in AI, we compare an outcome with its ground truth, right? We either compare an image or a video or a document with their ground truths, or we sometimes take a human perception as a benchmark about a specific outcome. But hardware doesn't work like that, okay? Because a chip has hundreds of input signals, hundreds of output signals, a lot of intermediate states, and they all interact with each other. And obviously there's memory unit, and they have to interact with the memory as well. So for example, if we take a simple example of an adder, a chip that adds two numbers. So ideally what we have to do is to verify all the possible pair of two numbers that a processor can receive. But practically it is not possible, so we have to be smart enough, and we have to make sure that we tested just enough combinations, enough boundary conditions to be confident enough to say that our chip is functionally correct. But and obviously we should also be checking that the memory is behaving correctly at every step, right? And here's the interesting part. So this flow may completely change from one design to another. For example, a processor has one set of requirements, but on the other hand, an NPU, a neural processing unit, has entirely different layers of complexity, new operations, new data flows, new boundary conditions. So we have to change our validation pipeline for every new design. So basically, our pipeline doesn't just run a fixed test, it has to understand the design, cover all the critical paths, and produce a score that actually reflects the real world silicon quality. So yeah, this is the hardest part of what we do. And honestly, I think this is where we spend most of our engineering efforts. So I think I just scratched its surface. Now I would like Kamer to talk about the technical aspects. Kamer, you may please share your screen. I'm gonna stop sharing my screen.
Yes, so hello everyone. Let me just share my screen so that I can explain it clearly. By the way, if you have any question, please note those questions down, or you can ask right away so that we can answer those questions by presenting our presentation. So I hope that you can hear me properly.
I'll hear you properly.
Okay, that's good. So as Musa has already explained how different it is to validate a hardware and how complex it is when we compare it with the validating a software. So at ChipForge, what we are doing is we are asking the miners to design a hardware, so we will have to have a full validation pipeline to validate the hardware that the miners are going to submit. So let me just give you some basic idea how about our validation pipeline, how exactly it works if we go into the deep detail. So first of all, let's say if we want to design a processor, okay, and what we will do, we will create a specification document for that with the detail, okay, how much instruction this processor should support, and other specific spec like in how much cycle we are going to access the memory, what speed is requirement, what area we need, what is the maximum area your design can have, and what is the maximum power your chip should be using. More than that, it's not allowed. So once we have given that, we have created that spec, we launch the challenge for the miners, and miners are going to compete. So before we launch a challenge, first of all, we have this question, okay, once we launch this question, the miners are going to submit the hardware, not software, they're going to submit the actual hardware, which is going to be described using hardware description language like Verilog or system.
Example of a question that would be queried to the miners regarding forging a chip.
So I am not. Can you please repeat what you were saying, because I think I missed start of.
Sorry. Can you give us an example question which would be put out to the miners?
Yeah. So let's say we want to design an adder. So we will give a task to the miner. This is just a basic example that I'm giving. So we will give that as a task to the miner by saying that, okay, you are required to design this adder, 64-bit adder with the 2 inputs, okay, and then 1 output. So, and your design should pass all the possible cases. So your adder should be working correctly for all possible inputs A and B. So this is an example of adder. And we will give them the detail about what maximum area their adder can have, what should be the speed at which your adder should operate, and what should be the maximum power that this adder can use. Okay, so this is about the adder. So now let's say we talk about the processor. The detail is going to be much more complex because the processor support, let's say 150 and 200 different instructions. We are going to give the task to the miner, okay, challenge to the miner, okay, you are required to design this specific processor, and it's going to be RISC-V based, and it should support these specific instructions. Okay, so let me just stop it here and give just go to this. Okay, so this is the RISC-V. These are the instructions from the RISC-V ISA. So as an example, we will ask the miners, okay, you are required to design a processor that supports this RV32I base instruction set. Okay, so and we will give them the list of those instructions that their processor should support. And then they will design the processor that support all those instructions with those load up, intermediate, and I don't want to go into the technical detail where we are reading from the memory, writing to the memory, doing some arithmetic operations and some operating system related instructions. So this is how we are going to give them a task. And then miners are going to give us the adder or the processor. And once they have given us the processor, what we are going to do is we are going to validate and check if this processor is correct. First of all, we will check if that is correct. Okay, this means it can execute programs correctly. That is the first thing that is very important. And once it's correct, we will check the other things, which are, okay, what is the area of this design submitted by the miner or the processor? What is the performance, like what is the maximum clock we can hit on that processor? Can we go for 2 giga or not? And what is the power utilization of that processor submitted by the miner? Now let's talk more clearly about the first thing, which is checking for the correctness. So once miner have submitted the design, we are going to check if their processor is executing all possible programs correctly. What does it mean by that is just like I have shown you the example of RV32I instruction set where we have about 20 to 30 instructions. We are going to check if that processor can execute all of those instructions correctly. Let's say we start with the basic instruction, which is an add instruction. Okay, just to check if the processor can execute that add instruction, we are going to write a test case with, let's say, add 2 and 5, and then add 9 and 9, and we will continue. But where can we stop in this case? Because if we talk about a 64-bit processor, okay, input A is 64-bit, input B is 64-bit, so the total possible combination for that add instruction only is 2 power 128. If we talk about 10 power, it is 10 power 38. So this is only to test all possible cases for the add instruction. And if we try to test it actually rigorously like that, even on the GPU like from NVIDIA 5090 is going to take 10 power 17 years, which is more than the age of the universe. So of course we are not going to do that. Otherwise, we won't be able to even test if processor can add correctly. What about the other things? What checking if processor can write to memory, read from the memory, run operating system like FreeRTOS, ossified? So what we do is, instead of covering all the possible cases, we use the intelligence and see what are the main possible cases that adder should operate on. Like it should be good enough, it should correctly add the small number, it should correctly add the large number, it should correctly add the negative and positive number, negative and negative number, and those numbers that could cause overflow. And similarly, those kind of possible scenarios we first of all create as a verification team, and then we run those tests. And similarly for all other type of instruction. So you can see even testing that basic processor extension, which I have shown you here, RV32i extension, is going to take some time, and at least we will have to test it for 14-15 million instructions to make sure that the processor that the miners have submitted is first of all correct. Once we know that, okay, this is correct, then we will move on to the checking other thing, which is, okay, we will check what is its area, what is its power, what is its maximum frequency on which it can operate on. So I will talk about that PPA, which is power performance area thing, later on as well, when I talk about the NPU in detail. So now you may ask a question that, okay, you are telling that, okay, it's very hard to run ChipForge, it's hard to validate the design submitted by the miners. Then what have you done by now? Like, if it's hard, then what will you be able to do? Will you be able to do anything at all? So the answer to that is this ChipForge MCU that we created totally using decentralized competition. So we launched multiple set of challenges, and we gave those as a task to the miner. First of all, we gave the task to the miner to design this RV32i, to design a RISC-V processor that support this RV32i instruction set. And I have already shown that this is the RV32i, which cover about 20 to 30 instructions. And then continuously we launched other challenges to support multiplication and division, and then compressed instructions, and then AES, SHA256, and so on. So we have designed this MCU. Although it's just the main processor of that MCU, the whole MCU is not yet complete, but we have designed that totally using decentralized competition. And we have even open sourced that on the GitHub. If you see it on the GitHub, you will find this ChipForge MCU. And we have added the whole guide that anyone can use to clone that repository. First of all, and install the required tools that are needed, and even verify this MCU that we have open sourced with the test vectors that we have already provided in this repository, along with the verification environment as well in this verif directory. So this is the NPU that we have built totally using decentralized competition with a set of 4 to 5 different challenges. Now, let me just concisely describe what is our main goal about MCU, like what we really want as an MCU. So if you look at this block diagram of our MCU, this is the target MCU that we want for the IoT applications. And for that, you can see the big block in that is the processor, and then we have memories, interconnects, and then some peripherals. So currently what we have designed is this almost 80% of this processor, although some planned extensions are yet remaining, like floating point and PQC. So if we talk about what we have done currently is we have added this extension for cryptography. What it is we are accelerating the AES encryption and decryption in the hardware, and also the SHA256, SHA256 as well. So what it enables is our MCU helps you to accelerate the encryption and decryption on our IoT devices. If we don't have this accelerator, it's going to take some time to encrypt and decrypt. So this is one thing. And there is another thing that we have planned, which is not yet completed. This crypto accelerator part with AES is already complete, but there is other very important part. By the way, I'm just continuously just presenting. If you have any question, you can stop me and ask.
Questions that have been coming via the chat. Did you want me to read some of them through now, or do you want to wait till?
I think, yeah, we can just continue the presentation, and then I was just saying that if you have some questions specifically from this presentation, or the audience have the question, they should ask right away. So it will be better to just answer it while I'm explaining. Okay. So so there is other very important thing in terms of security perspective, that is the PQC accelerator that we have planned in the phase 2. In the phase 2, we have planned some floating point extension and another extension to support the operating system so that an operating system can run on our IoT MCU. And then there is this PQC accelerator that we have planned. What does this PQC accelerator mean? Is post-quantum cryptography accelerator. So if you have some background of the security and the way encryption decryption work is, we have two type of encryption, that is symmetric and asymmetric. So symmetric is the AES, which is very strong, not easy to break, but but not easy to break only if those keys are secure. So if we want to send those keys somewhere, we will have to send those keys securely. So to securely transfer those keys, we need to use some kind of secure method. So for that, there is already asymmetric cryptographic algorithms like RSA and elliptic curve that are already being used in banking, and even Bitcoin uses that, even the Bittensor uses that. But there is a huge problem in that all the security analysts have analyzed, and that is that you can generate the private key from the public key using Shor's algorithm if you have enough compute power. Currently, we don't have that compute power for sure, but we know that the quantum computers are coming, and according to Google, by 2029, the quantum computers are going to be there, and they are going to for sure break the current cryptographic algorithm. So what security analysts want is, they want to secure our future. So they have already built this PQC, post-quantum cryptographic algorithm. Okay, and the softwares are already being changed so that once quantum computers come, they don't break the current system that are running. But the thing is, the only solution is not in the software. We have to accelerate that PQC in the hardware as well, because its key is huge. Its algorithm is so complex that it takes some time. Okay, so instead of doing that totally in the software, we have to have a specific accelerator in the hardware. Just like AI, like we cannot run AI in the software only with this basic processor. We will have to have an NPU, TPU, or a GPU. Similar to that, cryptographic algorithm like PQC need a accelerator like PQC accelerator in the hardware. So that's what we have planned for the MCU. Okay, so this is just to show what we have already built in the term of MCU and what is remaining and what we have planned for the future. So this is about our MCU, and if we talk about the main idea why we started the ChipForge, that was for AI acceleration. We saw that currently a lot of work is being done in the software, but in the Bittensor there is no work being done on the hardware to accelerate the AI, to reduce the cost of the hardware on which the AI is going to run. So we started working on the NPU in the November, and then instead of starting from the very scratch, we saw that the Google open source is Coral NPU exactly at that time, at the end of November 2025. And we say, okay, why not we start from that NPU, take that as a baseline instead of building that from the very scratch. So to just give a concise overview of the NPU, it has a scalar processor that even the MCU have, but it also has a vector processor where we can do vector addition, multiplication, MAC operation to accelerate the AI algorithm. And even we have this matrix processor which can do a lot of MAC operation that can accelerate the CNN and to truly accelerate the AI algorithms if we run those algorithms on the edge devices. And this NPU is specifically for the edge devices and for the inference. It's not for the training, because for the training you have the TPU and the GPU. Currently, the market that we are competing on in terms of the NPU is the edge devices that are ultra low power. So we started working on that NPU, and at the start we say, okay, we have to give some challenges to the miner. We understood the current NPU that was designed by the Google. We understood that, and then we saw some weak points in terms of some missing extension in the vector processor. So the plan was, okay, we have to add those extensions, and the miners are going to help us add those extensions. But if we give this as a task to the miner, the question comes is, once they submit it, how will we validate it? We will validate it with a verification environment and the test cases. But we don't, at that time, we don't have those test cases. So, and the verification environment. So at the end of November, we started working on that NPU from the Google, and we started creating our verification environment, and we started creating our own instruction generator to generate millions of instructions on the go. So while we created the verification environment and that test instruction generator, we tested that on the Google's NPU, and we found some issues in the NPU in the Google's NPU itself. So if we just show it to you, this is the repo from the Google that is open sourced. And actually, when we created our verification environment and we created our own test cases, when we executed those on the NPU, we found some multiple bugs. So we communicated that with the Google's team, and then we fixed those bugs, and this PR has already been, and our change has already been merged into the main branch of the NPU. So this also shows that our verification, although the verifying the chip is very complicated, we have already described that, but it also shows that our verification environment and our validation pipeline is industrial grade. We are doing exactly like big companies are doing, because we have broken the NPU from the Google, which even the Google team was unable to find that specific bug because they have already started working on that NPU about 1 year ago. And it's not just the end. We continue working, and we generate more and more test cases, and we found another bug, which is in the PR71. And that bug is actually more complicated, and we are still working on that and trying to fix that. So this shows that we have found multiple bugs from the Google team, and we have fixed some of those as well, just to show that our verification environment is such a rigorous environment, and that's how we are working on the NPU. So this slide just shows what I've already described about our work on the NPU and using the Google's NPU as a baseline and continuing working from that. So we have two parallel tracks. I have already described that MCU is one of the tracks where we are working on. That is for IoT and embedded devices. And the other is for AI, which is the neural processing unit, specifically for ultra low power edge devices. Tiny edge devices that needs some intelligence on the edge devices. For that, we have created that NPU. So let's talk about what we have done so far. I have already described that. And in this whole workflow, we have just said that miners were contributing in designing the hardware. We have already said that hardware is about designing and then verifying it. Currently, in those previous challenges that we launched, the miners were contributing in designing those hardwares. So what was happening is they designed the hardware. Our ChipForge verification team create a huge amount of test cases. We provide those test cases to the validator, and then validator use those test cases to verify the design submitted by the miners. So here is the catch, that to verify a chip or a processor complicated as the one we are working on, the 14-15 million instruction is not enough. But currently we are working, the validators are only testing it for 14 to 15 million instructions, because they cannot test for more instruction. Otherwise, just once a miner submit their solution and the validators try to validate it, if it validates for 14 to 15 million instructions, it is going to do that in 5-10 seconds, or 5-10 minutes. But if we try to rigorously test it with the billions of instructions, which is actually how a processor is verified, it's going to take a huge amount of time. So we don't do that. Instead, validator first test it with the basic 14 to 15 million instruction set, and once they have found the winner design, and then that design come to the ChipForge team, and then ChipForge team continue to further test it for weeks and weeks, okay? So that we get a good coverage. We at least test the design for billions of instructions to make sure, okay, this is correct, and this is not going to break once we tape that design out, and it's in the customer market, and the developers and others are going to use it. So this is how it was happening. But what we are now going to change from now onward is, instead of miners only designing the hardware for us, they are going to help us in the verification as well, because verification takes most of the time. So we want to reduce this time. So what's actually going to happen in that is, once the design from the miners is there, we have a winner design. Okay, validator have seen, okay, this is the best design. We are going to give set weights for that. This miner is going to get emissions. Once that design is finalized, we are going to give this design again to the miners, but now with a different task, that is to verify this design and break it. What does it mean by that? The miners are going to generate more and more instructions, and they are going to try to break it. The one who break it earlier will get the reward. So this way, they are going to try to break it. They are going to generate millions and millions of instructions. So if we have dozens of miners, we can get this coverage, which is billions, verifying that processor and the billions of instructions at fast pace, instead of only ChipForge team working on that. Now, let's say we have given this as a task to the miner to break it, and one of the miners has generated a test case, and that test case is actually breaking the hardware. This means processor is unable to execute it properly. So this means we have found that bug. And then the validator are going to check using automation, okay, is this really a bug? Once we know that it is really a bug, the ChipForge team is not going to solve it. Then ChipForge team is going to create another challenge, which is, okay, now you have broken the processor, let's fix this bug. So miners are going to fix that bug. Once the miners have fixed that bug, where again the other miner may found another bug, okay, so this loop of breaking it and fixing it is going to continue, and this is the part where 70% of the time is actually spent in the chip design. So this is how things are working from our end, and what we have planned for the future, so that we speed up the chip design. If we speed up the chip design and reduce its cost, it's going to be easy for us to sell our MCU, our NPU in the market, because those are the tiny devices and the cost is a big factor for those. If we move from the, let's say, $10 to $12 per chip, that's a huge difference in if we see the NPU, edge devices, and the IoT devices. So this is what I have explained currently. And at the start, I discussed about when miners submit the design, we check if it's correct, and then we also check about area, power, and its speed. Currently, we were talking about the correctness part. Once we know that all the bugs are found and all the bugs are fixed, this means that the design part is complete, which is actually the front end of the chip. So once the front end of the chip is complete, actually in the front end what we do is we describe the chip using HDL language. Just like Python is one language, C is another. These are programming language, but we describe the hardware in hardware description language. Once the hardware is there in terms of HDL, we generate actual hardware from that. This means we convert this to the transistors. So when we convert this to transistor, then we get to know, okay, what is its area? Because we know the area of the transistor, we know the separation between the transistor, we know how much power those transistors are going to use, we know the speed at which current is going to flow from those. So this way we are going to get to know, okay, what is the area, what is the power, and what is the performance of the chip that is submitted by the miner. So we check for the correctness, and also we check for the PPA, power, performance, and area as well. And then we finalize, okay, this specific miner is the one with let's say, with a good area and a good speed, 2 gigahertz, and very less power, like 15-20 milliwatt. So I think this is it from my end. I think now Abdullah can continue from here. And if you have any question from me, right away you can ask, or otherwise we can complete the presentation and just continue with the AMA.
Thank you so much for that. That was super descriptive and yeah, quite informative on the validator and miner side. I can actually see that there's been a lot of questions asked, which is great. So we'll go through them shortly. I just wanted to ask you, before I ask everyone else's questions, what kind of background does someone need to become a miner on ChipForge? It seems quite complicated, and I would love to understand that.
Yeah, that's a great question. And actually, we really want the miners to engage in the subnets, and the more miners we have, the earlier we will be able to verify and break the chip and find bugs earlier. So you don't need any GPUs and those kind of things. You don't need a huge amount of computation power like other subnets. So what you need is you need a hardware background. That's it. So if you have a good hardware background and you know how to design a processor and basic understanding of that, you can be the miners at ChipForge, and you can mine here. Yes.
Thank you for sharing that. So there was a question that came from Felix that I was going to also ask, which was, Winner takes all sounds intense and gets killer designs, but it probably scares off a lot of solid engineers who don't want to risk weeks of work for zero payout. Have you thought about mixing tiered rewards, bug bounties, or ways for people to get paid for incremental improvements?
Yeah, that's a very good question. And we got this question earlier as well. And actually, the thing is that, let's say we got multiple designs from the miners, and one is operating, both are correct, okay? Both have the same area, and both are utilizing the same amount of power. But one is working at 2 giga and the other is working at 2.2 gigahertz, okay? So, of course, we are going to go with the 2.2 gigahertz and continue working on that. But what is the use of 2 giga design for us? It is totally useless for us. And we cannot continue working on that 2 gigahertz design as well in the parallel, because working on those two design in parallel is going to, time-taking thing. So we just want to focus on that best design that we have, right? So that's why we just give the mission to the miner that give us the best design. That was the case as of now because of the design part, because miners were only working in the designing. Now, as I have already described, that from now on, the miners will be working on the verification as well, where they will try to break the chip. So it's not that the chip has only one bug. At least any chip that we designed at the start, even by the top hardware design engine, has thousands of the bugs. So if we give the verification task to the miner to break it, multiple miners will be able to break that design. So all of the miners will get the reward in this case based on how much bugs they have found. And similarly, how much bugs they have found fixed. If we give a bug fixing challenge, here as well they can get the reward. So this verification part is going to give emissions to multiple miners for specific challenge for sure. But the design part was complicated, and only the one with the best design can get the emission, because other designs are just, we cannot do anything with those.
Perfect. Thanks for that. Uklu says, beyond token emissions and inflation, what is the concrete plan for generating external real world revenue, and when exactly will this start flowing back into the ecosystem? And compared to competitors' names, existing features, where exactly does your technical architecture diverge? Why should a developer or user choose your stack over theirs?
So basically, let me get to the question. We have planned for like revenue, but we have to go long before that. Currently, we are in a sort of R&D phase, but once we are done with MCU and we fabricate, there will be definitely revenue, and huge revenue. If we look at the hardware side of things, the rewards are too high, but they are not here in like short term. And we are also planning working in like background on doing some subscription based model for the verification of different design. But I guess I should not talk about that at the moment, because it is in under consideration at the moment.
Perfect. Thank you for that. Messiah asked, for someone brand new to hardware design, maybe they only know software or basic Verilog, what's the fastest path to submitting their first competitive design? Either beginner-friendly challenges or starter templates planned?
I guess someone who have basic knowledge, so they should focus on agent-based mining, and I guess we are getting to the point that the agent will be getting and doing all sort of things, and so why can't agent do hardware design? So for someone with like less knowledge, if they have a good agent, they can definitely out compete humans. Not at the moment. We don't have any LLM at the point that can do it, but definitely in future there will be good agents and LLMs that will be very good at designing hardware.
And basically, unfortunately, we do not have beginner-friendly challenges or templates or components.
Okay. Thank you for sharing that. Sincerely V said, how do you intend to prevent people from gaming the system with optimizations that look good on benchmarks but don't translate to real-world performance?
I guess, as Logix has said before, that it's not like a software that can be gamed easily. Because for gaming, because there can be a millions and billions of different scenarios that how it can perform, and we have and gaming hardware is not so easy, and we have not seen it yet. For a challenge that is challenge 11, it was like for like 2 weeks, and no design was good enough to pass our threshold.
Let me add on to that. So the thing is, we verify the design with millions of instructions. Okay, so there is no possibility that miners can try to just game it out and try to submit something, some kind of a design that passes those test cases only, but actually is not correct. If the miner's design passes those test cases correctly, for sure it's going to be correct. And there are two things. One, and that is we give different test cases to the miners. So we give about 14 to 15 million test cases to the miners so that they can test it on their own end to check, okay, if their design is correct. And to the validator, those test cases are completely different. And you cannot try to create a false statement for all possible instruction to say, okay, if this is instruction, that is the output. This is that. This is not possible at all because the test cases for the miners and the validators are different. And also because there are huge amount of test cases, you have to, it's easy to submit a real hardware than trying to submit something that works and give you a mission while actually is incorrect. Spending time on gaming and trying to break our system is totally impossible. And if you can, if you try to spend some time on that, it's going to take huge amount of your time, and still you won't be able to do that.
Thank you for that. I'm just going to keep moving through them because there was quite a lot of questions. Karasoke said you mentioned fixing bugs in Google's Coral NPU through your decentralized verification pipeline. What exactly did the community discover, and how does that showcase the power of crowdsourced hardware verification?
So first of all, the thing is that our ChipForge team actually created the verification environment first of all. Okay, that is a verification environment that we create for every challenge, and then we created some test cases, and those test cases actually broke the NPU, and also we have prepared this challenge, which is the verification of Coral NPU, or in other words, bug bounty challenge, or challenge where the miners are going to break this Coral NPU, which has not yet been launched because currently there is a bug fixing being, which is the point number 3. We have launched a bug fixing challenge, and the miners are asked to fix that bug, which we have already found in the NPU. Once that bug is fixed, then we are going to launch this verification challenge or bug bounty challenge, where miners are going to try to break the NPU with more and more test cases.
I want to add a single line to this as well. So I think this is enough to showcase the power of decentralization, that we found those bugs and we fixed those bugs that even Google was unable to find. That's my take on it.
Thanks for that, guys. So how are validators incentivized beyond miners with the current winner takes all? Just, it's another question that's come through. Maybe it wasn't clarified.
If we look at the emission, latest how the Bittensor chain works, it's so that the validator that first find the new winner, it's get the more reward. And for validators, it's incentivized for them based on their take, that they will try to be the first in design, in validating the designs, validating the miners emissions. So it's in Bittensor chain that will encourage them to be the first in doing so.
Thank you. AI researchers are now fine-tuning LLMs to generate Verilog/HDL. How well are AI-generated designs performing against human ones on the leaderboard right now, and how do you expect AI to dominate chip design on ChipForge in the next 12 to 8 months? And I think on top of that question, I wanted to just ask where you guys see the team even in the next few years from now as a long-term kind of just roadmap.
I guess I have answered it before that AI generated designs are currently not performing against human. There is always need of human supervision. If a hardware design engineer is using AI for his work, he is definitely doing well. Then the hardware engineer, which is not using AI in as his assistant. We might get to the point where there are good LLMs for Verilog, HDL, and we will, and there is always a win-win for us because all we need is a good designs, and either it's AI generated or human generated. And I guess I was able to answer your question. Anything I missed?
Just more about also the future. What you think? Just on top of that, what you think long term? ChipForge will what will you guys be doing in 3 years from now? Or where
So
do you see
basically, we
ChipForge?
will be doing two things. Okay, I got your question. We'll be doing two things. One is a complete edge AI chip. So for that, we are trying to build NPU, and then we'll try to fabricate it. And obviously, before that, we'll try to integrate everything into a single SoC, and then we'll try to run AI models on the chip. This is our first goal, and the second goal is to build a complete decentralized infrastructure. And for that, we are trying to build an agent-based verification environment that would be, intelligent enough to adapt to the challenge, and it will be able to, validate every design with minimal human intervention. And the second part is we are trying also to build an open, decentralized verification environment where the people from around the world would come and submit their design. And obviously, this design will be secure, and the verification process will be fast since it is open. So yeah, these are the two main goals that we are trying to achieve in next couple of years. I think I hope that answers the question.
That does, and that's a very big feat. That's very exciting, and I'm excited to follow your journey, and I hope you keep us all up to date on that as well along the journey. Will there be an official announcement regarding a partnership or solution provider agreement with Google? Is such a collaboration currently in place?
No, I guess he get it wrong. So it's not like a partnership. Basically, while we were starting with the baseline for our NPU, we made our validation pipeline and it found bug in Google NPU. So it was a simple bug fix for our team. So we can maybe there might be partnerships in future, but currently there is no partnership at the place.
Thank you for clarifying that. What's the one thing community or miners are asking for that you're still figuring out how to deliver? Maybe better tools, different challenge types, or something else?
I don't get what he is trying to ask, but as I get it, that we are doing different things, but we are going in one direction, and that is the Edge AI and the chips for Edge AI devices. And we hope we will be get there in next years.
Hi. Can you guys hear me, please?
Yeah, we can hear you.
Yeah. So I actually joined 20 minutes, like 10:20. So from what I've been hearing so far, I know that Subnet 84 is a decentralized, semiconductor and some like a circuit design subnet. So I have a few questions that I would like to ask. I don't know, someone can I go on?
Yeah, go for it.
Yeah, okay, thank you very much. The first one has to do with dynamic DAO. So we know that basically every subnet, most of the major subnets that have been in Bittensor for the past 6 months are generating some flows or money in as revenue. But I want to ask Logic and his other teammates what is their off-chain demand, and is there any design that has been produced by any of the miners or the team itself that has been licensed by any external hardware firm, or has been integrated into any commercial product? So that's my first question, but I would like you to answer that for my second question. Thank you. Did you
Right
get me?
now, yeah, I get it. Right now, we are in
Okay.
process of it. We are getting to the point. We are making our MCU chip, and we are planning to complete it by year end. And when it's complete, uh, there will be revenue from it, and it will help us grow on our bigger goal, which is uh, NPU for edge devices.
Okay. Thank you very much. Now, so I was going through the questions asked, and I saw something like a winner takes it all. So I would love to ask, because of I know that some subnet owners usually have this mistake. So is at any point is the cost of the compute for an an unsuccessful design submission, does it outweigh the probability of you know winning a reward?
Sorry, I cannot get your question. Can you phrase it or repeat it?
Okay, so what I mean is that most subnet owners that do this winning statics of winner takes it all, because I saw a question there that talks about winner takes it all. So I would like to ask, at what point does the cost of compute of a successful design submission by a miner outweighs the probability of a winning reward? Do you get the question?
No, I cannot. Submit, can you repeat?
Okay. What I mean is that if I'm to join Subnet 84 right now, and I know that is a winner takes it all reward mechanism, and I'm to put in and I put in work, is the cost of that my compute, of that my compute, is it going to be more than you know the reward of the person that gets it, let me say, that week or that month?
Oh, now I get it. So basically, for mining or subnet, you don't need compute. You need skills, and the skill is hardware design. So you can submit your design with any machine without GPU. So there is, I guess, no cost for submitting a design and also that. You don't need to switch on your machine and it's keep running. That's happen in different inference subnets or uh, prediction subnets.
I think, Well, thanks for these
Okay,
questions.
okay. Okay, Subnet, you can go on. Subnet can go on, sorry.
I think we'll have to wrap it up soon. So I'm just going to ask maybe one more question that was written down in the chat. Will there be a mandatory staking requirement for validators or miners to enhance network security and ensure professional? Then finish the question. But will there essentially be a mandatory staking requirement for validators to secure the network, I believe?
No, there will not be. Miners don't need to like stake to a subnet for being submitting designs, and I guess it's a bit wrong, and some subnets were doing this, but it's not a good practice, and we are not going to do it.
Perfect. Well, thank you so much for joining us today, guys. Maybe I'll just ask one more question to close it off, which is, I wrote it down. I actually had a few questions myself, but the audience they had a lot to ask as well. Why should someone care about ChipForge? Why should we be why should there be importance placed on this subnet?
Okay, I think I would like to answer this question. So obviously, when we started, we didn't know this, but with the passage of time, we started realizing that basically hardware complements software and software completes hardware, right? So I think we should start normalizing it, that when we talk about, decentralizing software or AI, I think we should also be talking about decentralizing the hardware. I think, in our opinion, this is the true decentralization, where software and hardware both go hand in hand. So yeah, this is my answer to this question. That's why people should care about, Yes.
Okay. I have just one question. Sorry. I just have one question. Okay. So what is that one thing that miners, the miners and some community members have been asking for in Subnet 84 that the team are still figuring how to deliver it, or how would I say are still figuring out how to better the challenge or the tool. Do you get me?
Can you rephrase it, please?
Maybe we'll question. We'll get Sydney to write it in the chat, and we'll have it answered there. Okay.
Yeah, right. I will try to answer it there.
Yeah, perfect. Thank you so much. And was there anything that any of the team wanted to share with us before we end the AMA today?
Yeah, I guess that's all from us as of now, and it's a really good experience joining the AMA with you. Thanks for organizing it for us.
Absolute pleasure, and feel free to engage with the community on Subnet Summer. This is the biggest subnet discussion community in Bittensor, as you know. So this is a great place to engage with the community about what you're building, what you're doing. And yeah, thank you so much for joining us today.
Yeah, LogicX, are you going to say something?
No, that's it. I'm just going to ask, say to the miners that mining on this subnet is actually not that hard. You may be seeing it as hard from outside because you have not mined on that subnet at all. You don't need that much compute power, as already Abdullah has explained. And even if you have a basic knowledge of the hardware, those AI agents are already capable that you can use those AI agents to solve those challenges and at least get some good emissions on our subnet.
thank you so much for joining us today, guys. And yeah, we hope to see you in the community soon.
Thank you, Subnet.
Sure. Thank you for having us. It was a great time with you guys.
Perfect. Thank you. Take care, everyone.
Okay.